Suppose we have two lines, line AB and line CD. If these lines intersect somewhere, these lines are called oblique. If they do not intersect anywhere, they're called parallel. Suppose that we introduce a third line that intersects line AB at point F and intersects line CD at point G. This new line, FG, is called a transversal. When the transversal intersects the lines AB and CD, it creates a total of 8 angles. We will label those angles angle 1, angle 2, angle 3, and angle 4, angle 5, angle 6, angle 7, and angle 8, and their measures are shown below here. We can show either the measures or we can show the names, and you'll see these angle measures change as we move the lines around. When two lines intersect, as we have with lines AB and FG here, they form a total of 4 angles. Angles that are opposite each other are called vertical angles and have the same measure. So we have this angle right here, angle 1, and we have angle 3. And those two are opposite each other and therefore have the same measure, 63.4, 63.4. Similarly, these two angles have the measures of 116.6, 116.6, and again, the angles opposite each other here are vertical angles and have the same measure. With lines AB and CD, they create a region between them that is called the interior region. So this region that is below line AB and above line CD is the interior region, and angles that are inside that interior region, so angles 3, 4, 5, and 6, those angles are called interior angles. Well, not surprisingly, those two lines also create the exterior region, which is the region that is above line AB or below CD. In other words, it is exterior to the two lines. Angles that are in those regions are called the exterior angles. So we have angle 1, angle 2, angle 7, and angle 8. Those are exterior. Notice that the transversal cuts the plane into 2 parts. We have the part to the right and we have the part to the left. All the angles that line up on the same side of the transversal are called same side angles. So 2, 3, 6, and 7 are same side angles because they are on the same side as each other. Angles 1, 4, 5, and 8 are also same side angles because they are on the same side as each other. Angles on opposite sides, however, like 1 and 6 or 3 and 5, are called alternate angles. They are on opposite sides of the transversal. Okay, when we drew the transversal through our 2 lines, we created 2 clusters of angles. We have cluster 1 up here, cluster 2 down here. Angles that are in the same position in their respective clusters are called corresponding angles. So angles 2 and 6 are both in the upper right-hand corner of their clusters. Those are corresponding angles. Angles 1 and 5 also hold the same positions as each other, as do angles 4 and 8, 3 and 7. So each of those pairs of angles are called corresponding angles. Now let's look what happens when lines AB and CD are parallel. Notice that when they're parallel, the measures in the 2 clusters of angles are congruent to each other. So all corresponding angles have the same measure. So angles 1 and 5, 1 up here, 5 down here, have the same measure, as do 2 and 6, 3 and 7, 4 and 8. So we see that all those pairs of corresponding angles are congruent to each other. We also see that when we look at pairs of alternate interior angles, they are also congruent to each other. And by that I mean two angles that are both interior, and in this case on opposite sides of the transversal. So this angle right here, 61.2 degrees, and this angle right here, also 61.2 degrees. These two alternate interior angles also are congruent. This only happens when the lines are parallel, and if these angles are congruent, we know the lines must be parallel. Similarly, each pair of alternate exterior angles is also congruent. So we have angle 1 and angle 7, both measuring 61.2 degrees. And we have angles 2 and 8, also congruent, each measuring 118.8 degrees. Notice also that when the lines are parallel, same side interior angles are not congruent, but they are supplementary. In other words, their measures add up to 180 degrees. So as we look at these two here, we have 118.8 plus 61.2, and those together add up to 180 degrees. Even as we move the transversal, we can see that the sum of those two angles always remains 180 degrees as long as lines AB and CD are parallel. And if these angles are supplementary, we know that the two lines are parallel. Same side exterior angles are also supplementary. So angle 1 up here and angle 8 down here are supplementary, 125.1, 54.9. Angle 125.1, 54.9, again, adding up to 180 degrees. Okay, let's look at a few problems here. So lines AB and CD are parallel, and we want to calculate the value of x, given that the measure of this angle right here is 2x plus 9 degrees, and this angle down here is 5x minus 4 degrees. So what do we know about these two angles, given that those lines are parallel? Well, what we know is that these two are same side interior angles, which means they must be supplementary. That allows us to create an equation. 2x plus 9 plus 5x minus 4 must be equal to 180. Well, we simplify to get 7x plus 5 equals 180, 7x equals 175, so x equals 25. Substituting x in, we get 2 times 25 plus 9 gives us 59, and 5 times 25 minus 4 gives us 121. So the angle up here at E measures 59 degrees, and the angle down here at D measures 121 degrees, and again, they add up to 180, they are supplementary. Okay, let's look at another problem here. So again, AB and CD are parallel, and we're given the measures of angle AED and angle FCE. We want to find out the angles, the interior angles of triangle DEC. Okay, so let's take a look at what's going on here. Well, we know for one thing that these two angles here, because they are alternate interior angles, must be congruent. So if the angle up here is 61 degrees, then this angle must also be 61 degrees. Similarly, we can tell that because these two angles are together form a straight line, they must also be supplements. So that means that this angle right here, 69 degrees, we can get by subtracting 111 from 180. That means that we have two angles in the triangle, 61 and 69. When we subtract those two from 180, we end up getting 50 degrees, so the angle up here, DEC, must measure 50 degrees. So we've now calculated all three interior angles, and we were able to do so in part by using the fact that these two lines are parallel, and that therefore these two angles, angle AED and angle CDE, must be congruent. Okay, let's look at another kind of problem that involves parallel lines. So figure ABCD is a parallelogram, and it is defined as having two sets of opposite sides that are parallel to each other. So you can see as we move these points around that it remains a parallelogram. We have AD parallel to BC and DC parallel to AB. Again, that's what this symbol means, the two vertical lines, line segments, I should say. Suppose we draw a diagonal from A to C. Well, this line segment here is a transversal for not one, but two sets of parallel lines. So let's take a look at what that means. So first of all, we can see that line AC is a transversal for the parallel lines AD and BC. What that means is that the angle here, DAC, shown right here, and the angle ACB, shown right here, have to be congruent to each other because they are both alternate interior angles. And this remains true even as we change what this parallelogram looks like. But those two angles remain congruent because they're alternate interior angles. Well, we also know that it is a transversal for lines CD and AB. And again, we have two alternate interior angles. We have DCA and CAB, shown in red here. So those two angles also have to be congruent to each other even as we change the parallelogram. And what that means in the end is that since the two red angles are congruent, the two green angles are congruent, that the larger angle here, angle DCB, the corner of the parallelogram, and the other corner of the parallelogram, angle DAB, in other words, the two angles combined, those two angles have to be congruent. They're both equal to 60.7 degrees, which is equal to 29.5 plus 31.2. We could do the same thing and draw conclusions about the angle at D and the angle at B also having to be congruent to each other as long as this is a parallelogram. And again, we did that because we were able to see that diagonal AC is a transversal for the two horizontal vertical lines from CD and BA, as well as the two not quite vertical lines BC and AD.